afternoon. I welcome you for today's discussion on tutorials for week 8. In week 8, we have talked about the compressible flows and steam and gas turbine. So, I will do two problems today to bring out some of the intricacies of this week's discussion. And of course, as our practice is, we will give you the tutorial problems which I encourage you to work it out. So, the first problem states that at a certain location in a flow of air, static pressure has been measured to be 2.4 bar and the stagnation pressure is 3 bar. So, measurement of the total temperature shows it to be that it is 468 Kelvin. We need to find out the Mach number and the mass flow rate per unit area. So, let us start with what we have. We can say that the static temperature can be determined by the relationships of temperature and total stagnation temperature and the static temperature connected with the stagnation pressure and the static pressure. In the problem that we have been given, we know both the static pressure P and the stagnation pressure P naught, and we are also assuming the gamma to be 1.4 for air. And if we take it, then we can find out that the static temperature is stagnation temperature times P naught P by P naught whole to the power gamma minus 1 by gamma, and that gives me the static temperature to be 439.1 Kelvin. In the absence of work and heat interaction, we have shown you throughout this week as well as in the earlier discussion on thermodynamics that T 0 by T can be related with the Mach number as 1 plus gamma minus 1 by 2 times Mach number square. And from here, since we know both T 0 and T, we know gamma, we can find out Mach number easily, and we can get the Mach number from this relationship as 0.574. So, it also shows the justification for using a compressible flow relationship, because you recollect that Mach number greater than 0.3 is considered to be a compressible flow. Now, flow rate per unit area m dot is given by the rho times c, because we know that m dot is nothing but rho times c times a, where c is our usual nomenclature for velocity. So, this velocity can be determined in terms of Mach number we know. So, Mach number is nothing but c by cs, where cs is the speed of sound, which means that if I know the speed of sound cs, I can find out c, and cs can be found out by using the relationship gamma RT, and that gives me for the temperature we have 439.1 Kelvin as 420 meters per second. So, cs is 420 meters per second, which gives me c to be 241.08 meters per second. So, our next target will be to find out rho, and then we can find out the mass flow rate per unit area. So, we can say that the static density is given by rho by P by RT, and we get it as 1.904 kg per cubic meter when we substitute the value of P, which is 2.4 bar, and temperature which we have obtained as 439.1 Kelvin. So, now if we substitute this value of rho and the value of C we have obtained just now 241.08, we get that the mass flux or the mass flow rate per unit area is equal to 459.12 kg per meter square second. So, from this example problem, what we found is we use the relationship of temperature, static and stagnation, and we talked about static and stagnation pressures and their connection. We talked about the velocity of sound as we have obtained earlier in the theoretical discussions and connecting with Mach number. In the next problem that we are going to talk about, we will take a steam turbine. The problem statement is this: at the nozzle exit of a certain stage in a steam turbine, absolute velocity is 300 meters per second, which means in our notations C 2, which is the velocity with which the flow approaches the rotor. The absolute velocity with which the flow approaches the rotor is 300 meters per second. The rotor speed, that is a blade peripheral speed, is 150 meters per second and the nozzle angle is 18 degrees. Please remember that the nozzle's purpose is to direct the absolute velocity at a defined angle. So, this 18 degree corresponds to our alpha 2. If the sum of the rotor blade angle, inlet angle and rotor outlet blade angle is 176.5 degrees, we need to find out the power output from the stage for a steam flow. The sum of the rotor blade inlet angle and the rotor outlet blade angle is 176.5 degree. This is given, but we neither know rotor blade inlet angle nor rotor blade outlet angle, and we have to find out the power output from the stage for a steam flow rate of 8.5 kg per second. It is further given that we can assume W1 equal to W2. Also, we need to find out utilization factor. I will introduce the utilization factor through this example. It is given that C2 is 300 meters per second, U is 150 meters per second, alpha 2 is 18 degree. We do not know individually beta 1 and beta 2, but together beta 1 plus beta 2 is equal to 176.5 degree. We know the mass flow rate m dot 8.5 kg per second, and though we do not know the values of W1 and W2, but it is given that W1 is equal to W2, that is the relative velocity at the inlet and exit of the rotor are same, and we can draw the velocity triangle where C2, W2 and U. Please note that the U is same for both inlet and outlet, because we are talking about an axial flow machine, and we have the other component C2U, C2M and the corresponding component C1U and C1M are shown. As we have discussed in the last lecture that we can use the common base method and draw the velocity triangle one on top of the other with the common base. So, let us do the same thing here, and once we do it, we can find out that this distance is C2U, and please note that in this case C1U is also in the same direction. This is important. In the theory class we talked about the opposite sides, but here in the problem given it is on the same side. So, from the inlet velocity triangle I can get that C2U is C2 cos alpha 2, which is equal to 285.3 meters per second, and C2M is C2 sin alpha 2, which gives me 92.7 meters per second. So, we have got C2M and C2U. I can find out W2. How do I find out? If I use this right angle triangle, and then I can find out C2U minus U, that is this component. This is C2U minus U, which is nothing but 285.3 minus 150, and this is C2M square. So, W2 square is nothing but C2M square plus C2U minus U whole square, and that gives me W2 to be equal to 164.01 meter per second. And from the problem we know that W2 equal to W1, and hence W1 also is equal to 164.01 meter per second. And we can get the angle sin 180 degree minus beta 2. Please note that in our case beta 2 is this angle, and hence this angle is beta 2. Let us write down the beta 2. This is our angle beta 2. So, if this is my beta 2, then this angle is 180 degree minus beta 2, and hence I can find out sine of 180 degree minus beta 2 is giving me C2M divided by W2, and hence I get that beta 2 as 145.58 degrees. And also we know that beta 1 plus beta 2 is 176.5 degrees, which gives me that beta 1 is 30.92 degrees. Continuing further, we can say that C1U is U, C1U is this portion, C1U is nothing but U minus W1 cos beta 1, and we get C1U to be 9.3 meters per second. C1M is W1 sin beta 1, and we get 84.28 meters per second. and we see that C1 is equal to 84.79 meters per second. We get power equal to m dot u times C2u minus C1u, which gives me 351.9 kilowatt. Now, utilization factor. Let us try to understand what does the utilization factor try to tell you. It tells us that how much of the exit kinetic energy has been utilized. We do not want the exit kinetic energy to be at all present, we talked about it, but in reality exit kinetic energy is inevitable. However small it is not 0. So, utilization factor actually talks about how much of it we have been able to use it, and utilization factor epsilon is given as WBL, the blade specific work, divided by WBL plus C1 square by 2. Let us try to understand physically what it means. The denominator talks about that WBL plus C1 square by 2 is the total energy that has been either utilized or leaves with the exit fluid. So, if we say that WBL is converted into useful work, then C1 square is lost. So, the total energy is WBL plus C1 square by 2, and of which WBL is utilized, and hence when we substitute it, we can write WBL as half C2 square minus C1 square plus U2 square minus U1 square plus W1 square minus W2 square. It is a general expression I am writing. I will apply for the particular case of axial flow turbine now, but let us first write down the general expression. So, divided by half the same expression of WBL continues plus C1 square by 2. Since we are talking about an axial flow turbine, so we can say that U1 equal to U2 equal to U, and these terms drop off. In this particular problem, it is not generally true. In this particular problem, we have said that W1 equal to W2, and then this term also drops off. And finally, we have here one C1 square term with a minus sign, and here one C1 square term with a plus sign. These two also gets cancelled, and this half also gets cancelled. So, in our problem, this utilization factor reduces as C2 square minus C1 square, which is the numerator, divided by C2 square, and hence we get an utilization factor of 0.92. So, in this problem, what we try to do is we try to connect the velocity triangles with the power output, and also introduced a terminology called utilization factor. In the problems that are given in the tutorials for this week, you will come across similar problems on steam turbines, where also the enthalpy relationships that we have used you have to attempt. And I hope that this tutorial will put you in a firm footing for starting those tutorial problems that are given for this week. This brings us to the end of this course on fluid dynamics and turbo machines. This course, as you have gone through, was in 2 modules. In the first module, Dr. Shamit Bakshi talked about the fluid dynamics, the different aspects of fluid dynamics like introduction to fluid flows. He talked about the integral and the differential approaches, talked about the mass and momentum conservation equations, and also talked about the viscous flows inside the duct or over a flat plate. In the second module, we talked about the thermodynamics related with turbo machines. It is not a full fledged discussion on dynamics, but we talked mainly about what is relevant for the turbo machines course, but we touched upon the first and second laws of thermodynamics and introduced the concept of efficiency. At that time, we did not really talk about the efficiency of the machine, but we appreciated that efficiency of a real machine will not be 100%. We continued the discussion with the different types of turbo machines. We introduced how turbo machine can be different from the aspects of positive displacement machine, and then we talked about classification of turbo machines, and also in week 1 we talked about the dimensional analysis. We talked about also these velocity components leading to Euler's energy equation. We understood why the real fluids are not going to perform the same way as a Venn congruent or the ideal flow, and we talked about the different losses and the causes behind the deviations from the Venn congruent flow. In the week 7, we talked about the pumps and cavitation, and we talked about hydraulic turbines, and in the last week, that is in the week ending today, we talked about the compressible flows, steam turbines, and we also talked about what are the effects on the classification of the turbines as well as on the degree of reaction and velocity triangles. We believe that after doing this course, you will be able to connect the fundamentals of fluid dynamics that is covered by Dr. Bakshi, the mass and momentum conservation equations. For example, you can easily see now that the Pelton turbine bucket, which is having a large deflection, or the impulse steam turbine blades which are having a large deflection, can be explained from the momentum conservation principle, the linear momentum conservation principle. You can appreciate that Euler's energy equation is nothing but an outcome of the angular momentum conservation principles, and this course also talked about little bit about the compressible flows and the details about the incompressible flows. So, this course we believe that will put you in a strong foundation to take an advanced course in fluid dynamics or learn more about the turbo machines, and if some of you are practicing engineers, then you will also like to use these ideas and concepts of turbo machines in your regular work, where you are trying to design or make a design improvement of pumps and turbines or compressors. And with this, I come to the conclusion for this course on fluid dynamics and turbo machines. Thank you.